Hello.
Welcome.
Hello. In this video, we will explain our project to solve the Aquafin challenge in more detail. The project is a collaboration between two companies, which we are introducing first. Gemsotec is a Belgian solutions provider founded in 2017 based near Leuven. Our mission is to enable industrial companies to make their operations digital and smart. Gemsotec combines its knowledge of industrial operations with software development in order to create innovative solutions for the workforce of our customers. Our go-round application makes tasks, inspections, and instructions mobile. Another nice example is our intervention app, which is the ideal tool to manage interventions and make sure all relevant information is at hand and communication goes smoothly. Gemsotec works for companies such as Air Liquide, Essers, Olion, but also for organizations like the Fire Brigade of Antwerp.
Danubius is a Hungary-based agile software company focusing on data science, cloud infrastructure, and custom web application development. Our strengths include understanding the business needs and building solutions based on solid architectures with superior user experience. Our colleagues' experience gained in previous anomaly detection projects served as a good basis for this hackathon. As a nearshoring partner, we implement custom software solutions for, among others, Plantain, Nordhof, Allianz Insurance Company, Raiffeisen Bank, and the Hungarian subsidiary of KBC.
For this hackathon, Gemsotec and Danubius each dedicated two project members. Actually, it was the first time that Gemsotec and Danubius collaborated on a project, and it went actually very smoothly. So from Gemsotec, Geert and Stefan contributed. Geert has knowledge of operations, mainly from the chemical industry, and knowledge of maintenance and how the maintenance process is working. Myself, I was responsible for translating the business side to the data science part. From Danubius, Peter and Victor contributed to the project. Peter did the overall management of the project, and Victor was responsible of the data science part and documentation part. So actually he has spent most of the time on the project. We have added our CVs to the project documentation, so you can find more information there. And Victor will go on and explain the main results of the data science part of this project.
Thank you. Hello, my name is Victor Czanka. I will go through the data science parts of the hackathon. The first part is the data preparation. We received the raw data from Aquafin, and in our first step, we were able to develop a script which is unifying the data across all 4 stations. The data was originally in different formats. Some was in long format, some was in wide format, some had 4 pump stations, some had 3. We converted all the data to one format, which later on we could feed into the models that we were using. The second achievement in the data preparation part was the data separation. The original data was very difficult to separate, as can be seen in this PCA image. The blue ones are the non-anomalous data, the yellow ones are the anomalous data. Without any data preparation, the data is not very well separatable. However, with the feature engineering step, which are described in the document, we were able to achieve a state where the data can be separated into anomalous and non-anomalous data. This gives us high hope that the models will be able to separate the data as well, and we could achieve good scores. On the modeling part, we were trying out different methods. We were using unsupervised and supervised methods as well. We were using a Python scikit-learn library. Here, there's a visualization of a different methods available in this package. We will present in the document the SVM, random forest, and linear discriminant analysis models. The result of these models can be seen in the document. high level, the output is that in real time, we were able to separate and achieve very good scores across different models. Going back in time, in a sense, predict the anomaly early, the results were going down. We could still say that around 3 hours, we have good results. This means that 3 hours before the anomaly happening, we have high hopes of predicting that in time. Our conclusions and suggestions to Aquafin is to concentrate on data collection and preparation. More precisely, we suggest to find ways to include more parameters into the raw data set, for example, vibrations or any other parameters of the pump. We also suggest to use more data, longer timeframes, including more anomalies. That would help the models to generalize better. We also suggest to collect the anomalies in a more precise way, where they are assigned to pumps, individual pumps, and they are categorized so that data science projects would be able to use and maybe separate the anomalies from the anomalies that cannot be or can be predicted. On the method side, we suggest to create an environment where continuous model evaluation and improvement is possible. We also suggest to find the ways to group the different pumps or pump stations and develop different methods for them. We saw in the data analysis part that sometimes models cannot be generalized based on the pump types. Thank you.
In this part, we will explain how we would see a solution in production. As indicated by Aquafin, they would prefer to store the data in a private AWS environment. So it means that the data from all the parameters and the measurements which have been done should be synchronized with the SCADA system where all the data is stored. On the other hand, we think it's important to categorize events and anomalies that are and alarms that are taking place, and this kind of information is probably stored in Maximo. So it means that you also need to synchronize that part of Maximo with the AWS cloud environment. This way, all the data, improved data, extra data can be stored in AWS cloud, can be transformed to the right format. And from then off, the prediction model that we will supply can do its work. So that was what Victor will show now in a demonstration. Victor?
Thank you. So in our demo application, we developed a very simple presentation how a whole workflow could work in AWS. The workflow would start with having the input data, the raw measurements, inside an AWS bucket, partitioned by the pump stations, where all the data would be stored in its raw format. Once the data is there and continuously updated, an automation in AWS could execute the application that was created by us. This application would transform the data from its raw format to the standardized format, and after that would run the prediction. Once the prediction is ready, the data would be saved back into S3 using the same structure. Here one can see the generated HTML files, which would present the results. There would be one overview page where the active anomalies would be listed. Here, one can see on the left side the anomalies on the stations, which pumps are affected, when the anomalies was generated, and when the predicted anomalies coming up. There's also a visual representation using a map which shows the pump stations in anomaly and without anomaly. Drilling in to one station, one would see more detailed results on the individual pump station. there would be a high-level summary. It could integrate to a work orders application where predictive or reactive anomalies and maintenance tasks can be managed. Also, there would be information on the location and the high-level layout of the pump station. Furthermore, the visualization could include a visualization on different metrics which are relevant to the system administrators, like the water level, the different metrics on the power and the flow, and the time of the predicted anomalies. This application and solution could integrate to a more advanced intervention app. Stefan.
Yes, indeed. So once an anomaly is predicted, it comes up into the dashboard. And then somebody, so a technician, needs to do the maintenance. So it means he goes into the field, and with this intervention app, you can assure that he has all the information available and at hand when he's in the field. So it means that a work order will be generated in Maximo when an anomaly comes up, or the anomaly can also generate directly an intervention in the intervention app. So we have developed this intervention app before. We did that for the fire brigade of Antwerp, where it shows GIS information. There's also navigation included. And you can also integrate with document management systems, for instance, so that he has the manual of the pump or the technical sheet of the pump at hand. So that's what this intervention app would do. It would inform the operator or the technician, and you will have all information on the intervention. So as you can see, we have all the necessary skills and experience make predictive maintenance a reality at Aquafin, not only from the prediction part, but also from the data storage, the cloud infrastructure, up to the mobile worker part. So we look forward to go further with this project and to become your partner to solve this challenge.